Alors vous avez eu il y a quelques semaines, ceux d'entre vous qui s'en souviennent, l'excellent cours du professeur Carole Delporte sur les protocoles de population. Et aujourd'hui, Janna Burman de l'Université d'Orsay, on ne dit plus Orsay, non?
Paris-Sud.
Paris-Sud, l'Université Paris-Sud va nous parler des recherches challenges sur les protocoles de population.
Merci. So this distributed computing model, population protocols, has been recently extensively studied in the last maybe about 15 years. So the particularity of this model is the inherent asynchrony and very low resources of its entities in terms of memory, communication capabilities, and also computational power. More precisely, so I will recall the model. So more precisely, this is, we consider in this model a collection or so-called population of computational and communicating entities that we call agents. This population is of a known size n. These agents are a uniform, indistinguishable, finite state. And the memory is independent on the size of the population. These agents are anonymous, and they communicate by interactions. So, yeah, in a synchronous and almost unpredictable way. And in every interaction, the two agents actually exchange their internal state and move to their states to another state according to the transition function, which actually defines the executed protocol in the population. For example, with this model, the protocol will be a kind of, we would like to compute some global property, predicate or function eventually on the input values of these agents. For example, whether 10% of the population have an elevated input value. So there are many motivating examples to this model. So of course, in the domain of mobile sensor networks, where sensors are actually attached to some humans or to animals, like in this example, or to some mobile devices. But there are also many other motivating scenarios, and this model is appear to be actually useful also for modeling dynamics in completely different various fields. Like, for example, in social networks, we can model propagation with this model, propagation of trust, rumors, epidemics. We can even model in chemistry dynamics of molecules in reactions, and even games, repetitive games of n participants, for example, with this model. So we use a notion of, so a little more details about the model. We use a notion of interaction graph, which actually give us the possible interactions of agents. But in this presentation, and frequently, we assume that the graph is complete, meaning that the agents, every pair of agents can communicate. And then we also have to assume a kind of fairness assumption condition. Because if, like I mentioned before, if we would like to compute such global properties or realize some global task with these agents, we need to assume some fairness in the interactions, just to avoid a complete disconnection in the graph. So there are several frequently used such conditions with this model. And just for this talk and many times we actually assume a probabilistic fairness or probabilistic scheduler, we can say, according to which we choose at each step a pair of agents to interact according to uniformly at random, according to some uniform distribution. So let us assume this. So the main complexity measures that we are interested in population protocols are, first of all, space. We would like to minimize this space used by the protocols, by the agents in the protocols. And we measure it in a number of different possible memory states. And then we are interested also to minimize the computation time, the time complexity, until the stabilization to the correct output or behavior of our system. And we measure the time in terms of interaction, expected number of interactions, actually many times in terms of parallel such interactions, where we can consider one interaction like as n consecutive interactions. So actually the time is the number of interaction till stabilization divided by n. So this actually minimalist model, we can say, with limited resources, was motivated by understanding what we actually can do with such very resource-limited agents. And it was established, first of all, that what we can compute with them is exactly the set of so-called semilinear predicates, actually ones that we can express by Pressburger arithmetics, roughly arithmetics with addition but not with multiplications. This result was improved later and showed to hold also for memories of agents which are strictly less than log n memory bits. So in addition to this computational power limitation, there are many other things that we cannot do with these small agents. So we generally cannot terminate. Okay, we cannot detect termination in our protocols. We have to generally stabilize to the correct output. Then we cannot many times tolerate faults. It is, however, known and it's possible to tolerate a constant known number of crashes and transient faults, but many times any number of toleration of any number of transient faults is impossible. Communication faults and Byzantine faults cannot be tolerated in the original constant space model. And the stabilization time is, we cannot accelerate it as we like. So for example, it was shown that we can compute these semilinear predicates in a linear time. And there are some that we cannot compute faster. Okay? And a similar result was also proven for regarding the fundamental problem of leader election. We cannot solve it in a sublinear time with constant state space population protocols. I speak about that because actually after discovering all these limitations, scientists wanted to add more power to these small teeny agents and proposed different extensions to the model. And now I will actually review these extensions and the corresponding results. Actually, the challenges, we can say, of this subject. So first of all, to cope with termination, we can just say, okay, there are some applications where eventual stabilization to correct output is enough. And if not, there the possibility to extend the model, to add some power to the model, and some works actually proposed such extensions in form of oracles, which can be actually considered like distributed entities giving indications to the agents which are useful to solve the problem. So such oracles for solving consensus were proposed, a minimal such oracle in some family of such oracles. And also some more powerful oracle based on a leader allowed actually terminating population protocols in general with the power of Turing machine of logarithmic space. So a lot of works also considered extensions of the memory of agents for being able to extend the computational power of this model. So many interesting works has been done in this line of works. Just several of important results. So for example, it has been shown that if we have log-n memory bits in our agents, we can start already to solve non-semilinear predicates. Then if we have a little bit more memory, logarithmic size of memory that allows unique identifiers, we can already, so this is what was called the community protocol, so passively mobile machines model. We then can simulate and have actually a power equivalent to Turing machine with n log n space. And another extension that was proposed, so-called, resulted in so-called mediated population protocols, actually kept the uniformity and anonymity of the original model, but proposed to add a shared memory, additional shared memory to every connection, every agent pair, communicating pair, and this gave a power equivalent to a Turing machine with n to the 2 space, polynomial space. So we also concern about speed of computation, and we learned that if we add a leader to the population, we can obtain exponentially faster population protocols. We can compute the semilinear protocols predicates in polylogarithmic time, but here the notion of stabilization was a little bit relaxed, and we refer to this a lot of time as convergence. And then recently, without any leader, it was shown that using the same notion of convergence, but with allowing a small probability of error in the solutions, we can also get computations of population protocols in population of polylogarithmic time. In another line of works, we studied extensively two important fundamental problems in distributed computing, leader election and majority consensus, and we obtained very fast protocols less than log n to the 2 in both cases for both problems, in using actually asymptotically optimal state space for each problem. Okay, this is for the leader election, and this is for majority consensus. And now considering the other property, toleration of faults, we could tolerate, we are able to tolerate Byzantine faults, a constant known number of such faults, again with community protocols, using identifiers, using logarithmic memory in agents. We can also, with a combination of a leader and unbounded memory in agents, tolerate communication faults. And now let me focus a little bit more on the any number of transient faults, actually on self-stabilization. So in reliability critical systems, we would be interested to tolerate any number of any type of transient faults. Transient meaning that the faults stop to appear after some finite period of time. And these faults may bring the system to some arbitrary state. And the so-called self-stabilizing protocols should, from such configuration, arbitrary configuration states of the system, bring the system to eventually, barring additional faults, to correct configurations, and stay in these correct configurations, correct outputs, or correct behavior. So notice that differently from classical protocols, here we have to stabilize to the correct output, starting from actually arbitrary, any possible configuration of a system, contrary to the initialized, non-initialized, uniform generally configuration. So the designers of this model, of the population protocol model, have considered this subject, and in their first paper on the subject, they gave some isolated self-stabilizing population protocols, but what is important, they showed that leader election is actually impossible with the original constant space population protocols. And intuitively, actually, I think that this also prevented to give a general characterization of these protocols, of self-stabilizing population protocols, because for solving the similar linear predicates, the leader election was actually an important component in this computation. And following this negative result, some works proposed to solve the problem by extending the model with oracles, and we get a solution to this problem with a kind of leader absence detector oracles for arbitrary graphs, and in uniform fashion, meaning without any knowledge of the graph. And later, other scientists actually found that another extension again of the memory of the agents can also help to solve this problem. But we need an exact knowledge of the size of the population. So a very strong assumption, actually. In this work, they also gave a polynomial time solution to this problem. Some other works considered much more stronger models and solved the problem with less memory, with mediated population protocols and protocols where agents can interact and communicate in groups from 2 to k. And another approach was to solve these problems by relaxing actually the requirement of self-stabilization, but still using an upper bound on the size of the population. So this approach called loose stabilization, and it requires that the leader persists, the unique leader persists for some long time, for example, exponential time after stabilization, but not forever. And self-stabilization requires that it persists forever. And some lower bounds and efficient protocols in this context were proposed. So now let me compare this problem from the point of view of uniformly initialized leader election and self-stabilizing one, where we cannot have any stabilization, initialization. So actually, if we assume uniform initialization, for example, every agent starts like a candidate, leader candidate, with only one bit of memory and very simple protocol of only one transition rule, I can solve the problem. Any two candidates, leader candidates meet, and one drops off. Finally, I will get only one fixed leader. While, as I have mentioned before, without initialization, the self-stabilizing case is simply impossible in the same context of population protocols. And while for initialized leader we have a lot of work and polylogarithmic time solutions, for the case of self-stabilizing leader election, we have only one polynomial time solution for the moment. And in general, there are not many studies on self-stabilizing population protocols. The subject seems a little bit difficult. So there is a place, there is this challenge in population protocols to study the time efficiency limits of self-stabilizing leader election and other self-stabilizing population protocols. And an important question is also to generalize to give a general characterization of end state, for example, self-stabilizing protocols. And several words about some different, completely new challenges in concerning this model will be to adapt more the model to follow the technological advances, to adapt it to some new applications, a new phenomenon that are interesting to study. So, for example, we may imagine introducing knowledge of position in the state of the agents for modeling, analyzing a phenomenon like here of ants forming some figures, or we may think of drones forming some figures in the space. Then we can also think of other extension, actually in this case of the beeping restriction of the model, where we allow the agents to communicate in a very restrictive way, only by beeps, by merely detectable burst of energy like light, or for example, acoustic signal, for modeling, for example, some phenomenon like you see here of fireflies, or for example, some very low power sensor networks, future sensor networks. And we also may imagine population protocols helping us to understand and design microbiological circuits for future biological computers or some intelligent drugs. And just to conclude, population protocols is a simple and pretty convenient model allowing formal analysis for many real-world phenomena, and there are still a lot of open questions. This is a fertile field, we can say, and things to study. Thank you.